Welcome to the debate. Our subject today is, well, frankly, one of the most exciting astronomical finds in recent memory. Asteroid 2025 SC79. Now, this isn't just any space rock. It's what they call a twilight asteroid, and it's got this incredibly fast 128-day orbit. It's racing around the sun faster than any known object of its kind. So the big question for us today is this. Does finding SC79 really force us to fundamentally rewrite how we understand our inner solar system? Or is it more of a critical refinement, maybe confirming a population of asteroids we sort of suspected was there but couldn't see? I'll be arguing that, yeah, this discovery really does demand a radical revision. We might need to, toss out some older ideas about how things formed and stay stable in there.
And I'll be taking the position that while SC79 is certainly a significant find, no question, it primarily fills an observational gap we already knew existed. I don't think it quite overturns fundamental theory.
Okay, I appreciate that view, but I have to say, the claim that SC79 forces a theoretical rewrite feels entirely justified to me. I mean, just look at the dynamics of this thing. An orbit completed in just 128 days, that's quicker than Mercury, faster than any planet. It seems to me that alone requires us to think about new dynamical frameworks. How does something stay stable moving that fast, that close in, between Mercury and Venus? But the real kicker, the theoretical earthquake, if you like, is where it might have come from. This isn't just common space debris. They're saying its composition, metal-rich, ancient surface, suggests it's a pretty substantial chunk of a long-lost planet. We're talking about material from a body that had already differentiated, formed layers like a planet. That implies a whole formative history, potentially a massive one, that our current models for the inner solar system just don't fully capture. We could be looking at the remnant of a whole hidden family of objects. And the mass involved there, well, that changes the whole census of the inner system.
Okay, I hear you on the ornium coin, and we'll get back to that. But I just don't quite buy that finding one fast rock fundamentally upends, centuries of understanding orbital mechanics. Look, this discovery is absolutely a spectacular achievement in observation. Monumental, really. But I see it as confirmation, not some kind of upheaval. The main reason we didn't know about 2025 SC79 for so long is laid out pretty clearly. It was hidden in what astronomers call the twilight zone, right near the sun. Our telescopes are basically blinded looking that close to the sun's glare. So its absence from our catalogs wasn't a flaw in Newtonian physics or orbital dynamics. It was simply a profound observational limitation. Finding it now, with better techniques, confirms this suspected hidden family might exist. It suggests the population was mathematically possible, even predicted by some models, but just incredibly hard to actually see. So finding one closes that gap. That's refinement, isn't it? Extending our knowledge into a really difficult-to-observe region. And yes, the 128-day orbit is fast, very fast, but it still fits logically within the expected dynamics of the inner solar system between Mercury and Venus. It pushes the known parameters, sure, extends them, but it doesn't fundamentally break the physics governing those orbits.
I get the focus on the observational challenge, I really do. But I think focusing only on how we found it kind of minimizes the theoretical problems posed by what this asteroid is and where it is. Let's talk about that composition again. When scientists start throwing around phrases like fragment of a long-lost planet, we're not talking about finding a little pebble. We're potentially looking at the heart, the core, or maybe mantle fragments of a body that actually differentiated, something massive, metal-rich. That requires a large, complex body to have formed early on, and then, importantly, to have been catastrophically shattered. Finding a remnant like that in this specific, very tight, very fast orbit, well, that really demands we rethink our models of accretion and destruction for the innermost planets. What kind of massive event and when did it happen that could leave such a substantial piece in this particular orbit? That points to a planetary history that's far more complex and probably violent than just refining our current model suggests. It feels like it changes the whole story of how the inner system came to be.
It's a strong point about the composition, certainly. But have you thought about the other side of that coin? While the composition is fascinating, a planetary fragment, as you say, is definitely noteworthy, fragmentation itself isn't exactly a new idea in planetary science, is it? We expect large fragments from major impacts, especially thinking back to the early solar system or, the late heavy bombardment period. So for me, the real scientific punch here isn't just that a fragment exists, it's that a potentially quite massive, metal-rich fragment can maintain stability in such an extreme, hostile orbital neighborhood. If our basic physics was fundamentally flawed, or if the gravitational kicks from Mercury and Venus were as chaotic as maybe simpler models might imply, you'd expect an object like this, especially if it's got significant mass, to have been thrown into the sun or ejected ages ago.
The very fact that S79 is stable there, in that extreme location, actually seems to confirm our existing models of inner system dynamics and stability. The planetary fragment aspect just gives us, higher mass, metal-rich data points to feed into those confirmed stability models. It makes the models stronger, not weaker.
I'm not quite convinced by that reasoning, because it feels like you're trying to separate the dynamics from the mass and the history. The very fact that a remnant from a differentiated body, something substantial, is stable there implies something profound about the early history. It suggests the early inner system might have included a much larger, more massive population of bodies that then broke apart. That inherently changes the mass distribution we need to account for. Let me push back a bit on this idea of just closing an observational gap. You're right, the problem was visibility, the sun's glare. But if we accept that this bias didn't just hide one rock, but potentially, as the term suggests, a hidden family, maybe hundreds, even thousands of objects, then the consequences are far bigger than just a simple update to the census list.
Right, precisely. And if we knew, theoretically, that such a hidden family could exist based on our current robust theories, but was just incredibly hard to map observationally, then finding the first example does primarily close that observational gap. We didn't rewrite the laws of gravity, we just got better at looking near the sun. The breakthrough was observational technology, not a fundamental flaw in theory.
But the sheer potential mass implied by that term hidden family, that's what changes the theoretical stakes for me. If these planetary fragments, or whatever they are, represent a significant chunk of mass in the inner solar system that we just haven't been counting, it fundamentally messes with our calculations about the early solar system's total angular momentum and its whole collisional history. This isn't just tweaking a number, it's potentially adding a huge missing variable that's been left out of our dynamic models for decades. And let's not forget the practical side. The idea that some of these objects could eventually drift close to Earth and we wouldn't see them coming, that highlights a massive and frankly quite urgent gap in our planetary defense inventory. If this discovery changes the total angular momentum budget and forces us to revise our practical definition of near-Earth risk, well, that absolutely feels like a rewrite of our overall understanding of the inner zone.
I see the scale argument differently, though. While the potential total mass of this family is, yes, significant, the fact that we have now observed SC79 actually allows us to start constraining that family's scale within known dynamic limits. It helps guide the refinement process. We're using actual empirical data now to improve our estimates of mass in that previously invisible region. Look, if we had found an object that was somehow defying Mercury's gravity at that distance, or maybe its orbit was tilted wildly inconsistently with everything else in the inner system, that would force a rewrite of fundamental physics. But this object, however extreme its orbit is, still seems to be playing by the known rules of physics.
Okay, let's focus specifically then on that extreme motion, the 128-day orbit. I still maintain that being faster than any known rock in our solar system is the defining feature here that pushes us towards a theoretical revision. This incredible speed and its tight orbit really stretch the known stability limits for smaller bodies in the inner system, arguably beyond what was confidently modeled before. The fact this object can maintain a stable orbit there suggests the dynamic environment between Mercury and Venus might be, much more accommodating to these fast, tightly bound objects than we perhaps assumed. That forces us to recalibrate stability parameters, chaos modeling for that whole zone. That feels like a major adjustment to our picture of inner system dynamics.
I absolutely acknowledge the speed. It's the ultimate edge case, you could say, a really critical boundary condition. But I think its significance lies not in overturning orbital physics, but actually in confirming the robustness of our stability models at those extremes. We're confirming that objects pushed right up against the inner edge of the solar system can still find a stable configuration, even with the huge gravitational pulls of the inner planets. SC79 is giving us crucial, high-velocity data points that let us improve the precision of those stability models. We're confirming how strong the solar system's stability really is against perturbations, effectively extending the known map of where rocks can safely hang out. If we were truly rewriting the inner solar system map, we'd be finding things that actively contradict the stability constraints imposed by the terrestrial planets. Instead, we found an object that fits, albeit right on the edge, within those known constraints. It's a remarkable extension of the map, definitely. But the underlying framework, the fundamental fabric of that map, seems sound to me.
That's an interesting way to put it, though I'd still frame it differently. The challenge for me is that the extreme nature of the orbit, plus the clues about its metal-rich origin, taken together, suggest a formation history and a current dynamic reality that just weren't represented in our previous models at all. We didn't just find a random fast pebble. We potentially found a piece of a planet behaving in a way that points to a maybe profound oversight in how we calculated the early mass budget of this entire region.
And I still circle back to the idea that the scale of the observational barrier we just overcame is the key insight here. It allowed us to finally get empirical data to confirm theories that until now lacked that hard evidence.
All right, so to summarize my position, it's the combination of factors, the unprecedented speed, the compelling hints that this is a fragment of a lost planet, and the sheer implied mass and scale of the hidden family this discovery might represent. For me, these things taken together force us to fundamentally rewrite the inner map. We need new, or at least significantly revised, models for accretion, for planetary destruction events, and for long-term dynamical stability very close to the sun, all driven by this new piece of evidence.
And to quickly summarize my view, while 2025 SC79 is a phenomenal, exciting discovery, the main hurdle to finding it sooner was observational, that blinding glare from the sun. Its characteristics, including its really extreme speed, seem perfectly consistent with an expected, though previously unmapped, population of inner solar objects that our existing orbital physics always allowed for. So this discovery lets us refine our current theories, close a huge known gap in our observational census, and ultimately solidify our understanding rather than necessitating tearing it down and starting over.
Right. Well, regardless of whether we ultimately call this a rewrite or a major refinement, I think we can agree that the discovery of 2025 SC79 shines a really bright light on the complex and maybe surprisingly busy dynamics happening between Mercury and Venus. It certainly reminds us that the full story, the history, and the long-term fate of this silent traveler and potentially its family is still a vital area for future exploration.